All right, everybody, it's time for another installment of Real Analysis on the Internet. This is for my students in Math 350 this semester. I promised you I'd give you a little bit of extra input about this Bolzano-Weierstrass theorem. We covered it in class last time, but I didn't quite get a chance to finish everything I wanted to say about it, so I thought you might enjoy relaxing at home and watching this. So let me just say a little bit about this very, very important theorem, because we're going to be using it to prove other things later on in the semester regarding calculus, in particular things about absolute maximums of functions and things of that nature. So it's going to be important, and so it's worth really getting this down. There's two versions of the Bolzano-Weierstrass theorem. There's one for sequences, and then there's another one for sets. The one for sequences is really quite straightforward. It just says that if you have a bounded sequence of real numbers, a bounded sequence always has a convergent subsequence, right? So what that means basically is that if you take a bounded sequence, you can pick off a subset of that sequence that will converge. Now, the reason that this is true, I'll just remind you of the proof very briefly. Every bounded sequence, when you take a subsequence of it, still remains bounded. And every sequence has a monotone subsequence. So that subsequence will be bounded and monotone. So by the monotone convergence theorem, if it's bounded and it's monotone, it converges. So we have to have a convergent subsequence. Very easy to prove that, right? The Bolzano-Weierstrass theorem for sets is a little bit harder to prove, but I'm going to do it for you here. Essentially, it just says that a bounded infinite subset, S, of the real numbers has to have an accumulation point. Okay? In other words, it has to have a point such that every neighborhood of that point contains elements of S other than itself. Okay? It's very important that this set S be infinite. I've reminded you here this is not true if S is a finite set. Imagine there are only n elements in that set, right? Well, then I claim that whether X is in S or not, either way we can show that X is not an accumulation point of S. In other words, S has no accumulation points if it's finite. Why not? Well, if you take a point that's not in the set, then what you can do is you can take epsilon to be the minimum of all of the distances between that point X and each of the elements x1, x2, x3, and so on from the set. That minimum distance will be positive because X is not in the set, right? So the distance between X and any point of capital S has to be positive. And there's finitely many positive numbers in that list, and so the minimum of them is still a positive number, right? Okay, and then that allows you to build a neighborhood around X of radius epsilon that has no elements of S in it. Okay? That's what it means to say X is not an accumulation point. All right? On the other hand, let's say that you pick an X that actually is in the set, and let me just call it X1. Right? If you pick x1, then what you can do is you can just do something very similar. You just take the minimum of all of the distances to all of the remaining points of S. Okay? And you build a neighborhood around x1 that has the minimum distance between x1 and all of the other points. Again, the intersection of that neighborhood with S will be just x1 alone. It will not include any other points of the set besides x1. So again, x1 will not be an accumulation point. Okay? So if you take a real number and it's not in the set, then it won't be an accumulation point. And if it is in the set, it won't be an accumulation point. There are no accumulation points, assuming that your set S is finite. Okay? So you have to have an infinite set in order for this Bolzano-Weierstrass theorem to be true. Okay, I'm going to erase this. You can always rewind and look back if you need to. Let me go ahead and write down the proof of this Bolzano-Weierstrass theorem for sets for you so that we can try to make some sense of it. Okay? here's what we're going to do for the proof of this, because I didn't get a chance to do this in class. It's not too bad, okay? What we're going to do is we're going to let xn be a sequence. We're going to use the first theorem to prove the second theorem, okay? So we're going to take a sequence of distinct points in S. Call it xn. Right away, we're using the fact that S is infinite. If S was not infinite, we couldn't make a sequence of distinct points like this, okay? So we have a sequence, and remember that S is bounded, so xn is also bounded because xn is inside of the set S, right? So xn is bounded. All right, well, we have a bounded sequence. So there has to exist a convergent subsequence by the first version of the Bolzano-Weierstrass theorem. So by the Bolzano-Weierstrass theorem for sequences, okay, there exists a convergent subsequence. I'm going to call it xnk. And let's just say that it converges to, let's say, x. All right? So we have this. Now this x may or may not be an element of S. We don't really know that. But I'm going to claim now that whether it is or not, whether x belongs to S or not, it is an accumulation point of S. Right? Look at what we're trying to prove. We're trying to prove that S has an accumulation point. So I claim that I have found my witness that's going to show that S really does have an accumulation point. So X is an accumulation point of capital S. That's the claim. So what does that mean to be an accumulation point of S? Just emphasize this here. Well, don't really need to say that. It's obviously the accumulation point of S here. So how do I show this? Well, I just have to show that every neighborhood of X contains points of S other than X itself. Okay, so consider a neighborhood U sub epsilon of X, some arbitrary neighborhood. So this is for arbitrary epsilon greater than 0. Okay, so you just choose one of those neighborhoods. Well, the thing is that the subsequence here, xnk, this convergent subsequence, eventually gets inside of that neighborhood because of the convergence here. So since xnk converges to x, okay, eventually its terms lie in U sub epsilon of x, right? They eventually have to get inside of any neighborhood of x whatsoever. But that subsequence consists of points that are in S, right? So there you go. You have, and there are going to be infinitely many distinct, right? Distinct elements of that subsequence that are in S. So this is a non-empty subset. There's terms of the sequence xnk that are in the neighborhood and in S, and there's more than enough of them to go around so that you are guaranteed that there are points of S in that neighborhood other than just X itself. So that completes the proof. Okay? So that's the proof of the set-theoretic version of the Bolzano-Weierstrass theorem, which is just a sort of a generalization of the first one. But ironically, we use the first one to prove the second one. Okay, I hope that this very short little proof makes sense. If for any reason you have questions about it or it doesn't make sense, by all means, feel free to come in and ask me about it. I'd be glad to help you out. Okay, hope you enjoyed it. Thanks.